The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So Nat is new to this. He hasn't seen this project. What I'd like you to do is give a little presentation of what
Sure. So we figured we just sort of come down in order of the paper topics.
Sure, that's fine.
All right.
Should we all stand up?
Yeah, might as well. Yeah.
Alright.
So the paper topic that we're doing is basically a dynamical system. So you have, we'll do the case for 4 entries, but it generalizes pretty easily. So you have something that initially, we will start with a square, and we'll label the vertices A, B, C, D. And then we take one step in the evolution of this game. We put vertices on the midpoints of these, we connect these edges, and we label these new vertices with the absolute value of the differences of the old vertices. And we do this until we either reach 0, 0, 0, 0, or something else interesting happens. And so we talk about this game for vertices that are labeled over integers and real numbers. We talk about this game with 3 entries, 4 entries, lots of entries, and we looked at some of the properties of that. So one of the properties that we found was that the game with 4 numbers on integers will always go to the 0, 0, 0, 0 tuple. And the way that you can see that quite quickly is, instead of considering games over the entire integers, consider reducing this to a parity game. So we either have evens or odds here. And there's a lot of symmetry inherent in the square problem. Specifically, all of the group actions of the symmetry group of the square will give you equivalent games because they preserve adjacent neighbors. And so in that case, you can take a game A, B, C, D, and this is basically equivalent to the game B, C, D, A, and any other cyclic shift or vertical, horizontal, or diagonal reflection. And so what we do is we say, okay, let's look at the game. There are 6 possibilities, right? The numbers could all be even. The numbers there could be 1 odd number in here.
There were 8, right?
Should be, yeah. There are 2 evens, 2 odds like this. There could be a space like this, or you could have 3 odds or 4 odds. I think there's actually only 6 in this case.
Trying to remember, I think the paper has 8 cases. Professor Miller's looking it up.
Okay. I think
I
this.
think because of the symmetry there is only.
Yeah. No, I get what you're saying.
I think this covers it. I may be missing one, but I think the details are in the paper.
6.
And essentially, you can evolve this process, and you get some invariant that says, after at most 4 steps, I will reduce to a state where all the entries are even. Furthermore, at each step, we either know that the maximum number of the max of this tuple is either decreasing or staying the same. And so what you can do is you can say, after 4 steps, I've gotten everything even. And we also showed a lemma. We proved a lemma that said a game that is a constant multiple. So if I have a game A, B, C, D, this has an equivalent length to the game K times A, K times B, K times C, K times D, where length is defined as the number of steps it takes to reach the 0 vector. So with that lemma and this lemma, you can do a pretty short inductive proof that basically says, I'm reducing everything to an even number, I pull out a factor of 2, I have a smaller min than I did previously, and that'll get you to 0, 0, 0, 0.
And then keep doing it and you get another even number.
Yeah.
And then pull out.
So Yida showed some interesting stuff for the game with 3 numbers.
Yeah, sure. So for the 3 number game, it's basically the same thing, but now you have a triangle. And to prove that this game actually doesn't go down to the 0, 0, 0 game state, but it basically cycles. So it cycles in the form of 0x x. So any game that you can make up, so say you have 1, 5, 10, and you continue this game, you'll get to the cycle of 0xx, and basically we prove how to do this by a proof of cases. So there are only 5 cases that you can have with a game with three values. So I guess I can just list the cases really quickly. So the first case is if you have a game that is has 1, 0, and we're also proving only for non-trivial games. So a trivial game would be one that has anything of the form x, 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 right? So anything like that will obviously go to 0, 0, 0 state in the next step.
Does anything else go to 0, 0, 0? Besides x, x, x?
I mean, this includes the 0, 0, 0.
But are there any other states that would, if any, would go to 0, 0, 0? Besides
No.
that? So that's a real short, that's a little isolated
Yeah.
collection of games.
It looks to me like your example does.
Which one?
The 1, 5, 10.
This game?
It
So
just,
that goes to 1, 4, 5, the next step.
Yeah, I mean, I don't think it.
1, 4, 5.
And then 3,
3, 1.
4, 3.
sorry, 4, 3, 1. Right, and we can just write it out like right here because it's the same thing. 1, 2, 3, right? And then this goes to 1, 1, 2.
Oh, you're right, sorry.
And then,
Thanks.
so that's actually one of the other cases. So that's a case where you have one number that's the same. You have one number and then two numbers that are the same, which is this case. And this case, after you get to this step, the next step is going to look something like the first case. So all these cases reduce to the first case, and the first case is the case that cycles. And x, y, z is the other case, and then this is the fourth one, and the fifth case is going to be yeah, I think
0, x, y is the next.
yeah. When you have, do I have that one? So in the paper, we go through all the different cases, and all these cases reduce to the first case, and we prove that on every step of all of these games, the three-value games, the range, something we call the range, which is basically the difference between the maximum number and the minimum number in the game, will always decrease, and so by the same property of induction of this game, where we say that the maximum value always decreases. We prove that the maximum value or the range in the three-value game will always decrease, and it will always reach the first state, which is the 0xx state, and then it starts to cycle. So
Your
So
section 3 was for
Ah.
Rails.
So the next thing we looked at was the game on arbitrarily many entries over the reals, and I was looking in this section. Is it okay if I move over? So for this game, we'll denote the elements A1, A2, AN. So this is the Nvalue game with AI and just R. So basically, the interesting thing here is that there exist solutions that do not go to 0, 0, 0. In fact, there exist solutions of infinite length. And so one way to look at this is to say, so this transformation rule that we have up here looks something like, I'll do the 4-value, I'll do even the 3-value case because it's easy to see. ABC goes to absolute value of B minus A, absolute value of C minus B, absolute value of A minus C. And this is clearly not a linear transformation because the absolute value is not like a linear function. But what you can do is if you express a constraint that I'm going to order these from smallest to largest, then you can drop the absolute value and you can actually get the correct ordering. So in the case, let's just do the 3-value case. So in the case where A is less than B is less than C, then I have this actually goes to the tuple B minus A because B is larger, C minus B because C is larger, and C minus A because C is larger. And so with that being said, I can express this as a linear operator. So let this transformation be T. And then in this case, it's going to be minus A plus B, C minus B, C minus A. And so if I have some state that it has the invariant where the entries are listed in increasing order, and I left multiply by t, I'm going to get a state out. Now this isn't incredibly interesting because you're not guaranteed that the output state has entries listing in increasing order. But in fact, if you take an eigenvalue, an eigenvector of this matrix as your state, then you're guaranteed that you're going to have that invariant hold because it's a constant multiple.
Unless it's a negative eigenvalue.
Unless it's a negative eigenvalue. So you have to be careful that you select an eigenvector that's positive and real and has an associated positive eigenvalue. And so what I did in the paper is we generalized this to, this matrix structure holds. You have, -1, 1, -1, 1, and then the last row has a -1 here and a 1 in the bottom right. And we look at symbolically, we expand the determinant, we look at the eigenvalues and the eigenvectors, and we show that there is always a positive eigenvalue. Furthermore, that eigenvalue is bounded between 0 and 1. And it's associated with an eigenvector of all positive real numbers. And so that shows that we can always find a starting state, basically that eigenvector, that will get smaller and smaller and smaller in general, but it will not reach the zero vector. Another way to look, and then generating infinitely many such solutions, this is a linear transformation, so we can add any constant or scale by any constant scalar. Or we can also generate the 8 rotation or 8 group actions of D8 on it. So that's kind of cool. Zach will talk about counting things.
Yeah, so I'm going to erase a little bit. So I guess basically at that point, one of the things that we discussed was sort of determining the equivalence class. We didn't really take into account all the symmetry at first. And then when we were thinking about all the different rotations and everything on the square, I started to investigate sort of the size of the equivalence classes. So the number of games for a given, so we were saying for the integers from 0 to n, how many equivalent games are there? Or how many non-equivalent, right? So we didn't want to overcount all the equivalent games because A, B, C, D is also equivalent to B, C, D, A. Okay, so basically section 4 just breaks this problem down into 4 cases and uses combinatorics to count that specific number. So what I did was I broke it down into k is equal to 4, 3, 2, or 1, where k is the number of unique integer values in the tuple. Okay, so for the case where k equals 4, we're looking at a game of the form A, B, C, and D. And basically, we have can choose 4 ways to choose our 4 numbers.
We're going from 0 to n minus 1, I think.
So, I mean, in the paper, I set it from 0 to n, because
They have n plus 1 choose 4.
Yeah. Yeah, that's right. So we have the n plus 1 choose 4. We have the 4 factorial ways to order them. And then there's the 8 different symmetries for this unique value game. So that term was that. And basically we broke it down. Do you want me to go through every case? Okay. So I did all the cases, summed them up, and we got some expression that was proportional to n to the 4th, which was to be expected because if we just say how many tuples can we make, there's n to the 4th. So this sort of started to tie into what we did in the 5th section, where we looked at the probability distribution of the path length for a fixed n. So if we take all the games, we call them the 4 games. We didn't specify that. Yeah. This is the 4 game because there's 4 integers. So there's the 4 game over the integers. If we take all the 4 games over the integers from 0 to n minus 1, that makes it easier. From 0 to n minus 1, what does the distribution of path length look like? So basically the first thing I tackled was, does it matter computationally if we account for all of these symmetries and only look at the equivalence classes? Or can we just generate all n to the 4th games and look at that distribution? So the very first part of section 5 is discussing how the probability of getting, I have to think about how I argue this.
Basically, almost all games are unique, right?
Yeah, almost all of the games are of this form. And then in the limit, as like there's a limit argument as n goes to infinity. Okay, so this was, it's actually equal to 1/8 n to the 4th plus the other terms. So in the limit, as n went to infinity, we got 1/8. And so what this is saying is that although we were over-counting, God, how do I say this?
The number
It comes out to 1. All I'm showing is that the
What comes out to 1?
So, okay, what I'm trying to show is that if we calculate this distribution for the case where we look at all n to the 4th games, this distribution, this probability distribution on the path length, so this is like the path length, is the same as if we only look at all of the equivalent cases.
If we exclude the symmetric.
So if we computationally go through and exclude all of the symmetric cases. So if I have the game,
All of the symmetric cases meaning A, B, C, D, and B, C, D, A.
Yeah. Okay, so if I have this game here, it's equivalent to, we can just rotate every number one position, right? So this is one of the symmetries about the square.
We basically don't want to double count it.
And there's 8 total symmetries about the square. And so we can either only generate this game and add this to our path length count and then generate the distribution, or we can generate all 8 of these games
And you'll still wind up with the
and
same
we'll get the
shape as
same distribution
In a limiting case. Yeah.
in the limiting case.
Okay.
Okay, now that's important because if we are doing this on the computer and we say find the distribution for n equals 256 and we want to exclude all of these symmetric cases, I let it run for 5 hours and it didn't finish, whereas when we wrote one that just had all n to the 4th possibilities, we got this in like 10 seconds.
Sidebar, turns out it's actually much computationally more intensive to deal with the symmetries than just generate all the pairs. All the
So,
tables, yeah.
but in order to like say that we were justified in doing that, the first part of section 5 was showing why we're justified in just generating all of the n to the 4th possible games and determining the distribution based on that.
So it's an interesting distribution. It's definitely like bimodal.
Yeah.
And it's unclear why.
Well, and the thing that we like threw it in because it was incredibly interesting to me is that if we do the CDF, it goes like straight up. And right in here is 4 and 6 is like up here for path length, and this is 4.
So
This is for 4 value.
Almost
games are
all,
4 long.
yeah, almost like by far the majority are in the
Less than
region of
6.
4 to 6. Yeah, so almost all of them are less
It's
than
very
6.
strange. Most maybe more than 50% for very large n, even for large n,
Yeah.
4 long.
Mm-hmm.
Yeah.
It's really amazing.
And that just really threw me off a lot because for a while I was trying to work on generating a game of arbitrary length. So I was trying to come up with some way to like recursively build up this game. And I was getting it. I wrote a function that could do one step. I could get the previous step. But there was some property that I was missing because it would get a couple steps up and then something would happen. And when I reapply this transformation, it'd be like 6 moves long, and I'd ask for it to be like 15. So there was something that we didn't quite uncover yet that was sort of causing these games to converge even faster than we were expecting.
It's very interesting. Quite unexpected that
Yeah.
it seems to stabilize. I wonder if you could actually find that half of the games measured any way you want that do have length 4.
Yeah. That's interesting. Yeah.
Great.
Yeah.
Great. This was a really nice project, and it's fun to read the paper. Thank you for this. So I guess I'm going to talk about some of the math in it, and Susan will probably talk more about the writing in it. One of the things that's a big part of the paper is this idea of symmetry. And I think you could draw that out more and make it clearer what you mean by it. We talked about D and so on, but you know, it's interesting. If you apply a symmetry to this game, so there's a prior thing to say. This is a dynamical system as well, and you use a notation G sub n plus 1, and so on for the sequence of moves. You could also use a notation that sends you from one state to another state. And you do that when you use that matrix. You give it a name T, which is also a standard name for a transformation that takes you from one state to another. Presumably that's why you chose the T. So you could also have that same symbol maybe, or maybe a different symbol. Or maybe you want to use the symbol, grab the symbol T from the matrix and use it for that transformation and cast it more as a dynamical system. I'm going to get back to what I was saying originally, but that brings up another idea in my mind. I think you should distinguish between games and states. The game is the whole sequence, and the state is the things that you pass through. So you were enumerating states, really, rather than games. And to my mind, there's a big difference, because as Yida was saying, you can study all the games. That's sort of what you were doing here when you looked at the trivial game, right? That's a block of games of the whole orbit, but you were enumerating states.
Right.
So I think it would clarify things if you make that distinction. So where am I going with this? Now I've completely forgotten where I started.
We should have a picture of the square and show.
Oh yeah, right.
Like,
right. So there's the symmetry.
Yeah.
So there's a symmetry there, and there's also the transformation. And I don't think it's true that the transformation commutes with the symmetry. I think if you rotate the game and apply the rule, you're not going to get the same thing as if you apply the rule and then rotate the game.
That sounds right.
But
they're like they are. You can
sym-
transform them.
They are symmetric, but it's by a different symmetry.
Yes.
The result.
I guess it's. I wonder if it's just by the inverse symmetry.
Something. There's something there, but it doesn't matter, because, like you said, what really matters is that adjacency is preserved. And somehow, so there's a notion of equivalence of games, which is preserved by that symmetry. So, for example, the length of a game will be the same after you do, and that's what you care about. But I think all that could be brought out more clearly than you do in the paper.
Okay.
That was just, as I was reading it, I got confused myself about what are they saying about the symmetry arguments.
Okay.
That was one thing. When you were describing your approach and this eigenvector that gives you an infinite game of the reals, it occurred to me that you might be able to find a long game over the rational numbers by approximating that irrational
Yeah,
starting
that's sort of where I
position.
got the idea of the Fibonacci thing the other day.
Oh, is it?
Yeah, I was thinking like if you get some like rational approximation of this, it might, or even like an integer,
Did you pursue that at all?
Sorry?
Did you pursue that at all?
Not really.
That's okay.
It's busy writing the paper.
Yeah, no, absolutely, absolutely. You don't need to do more than you did.
Yeah.
But I didn't really appreciate that point until I saw the presentation here. That would be a great way to try to get at long games. Why'd you pick powers of 2?
For n, it fits in a cache line pretty well.
Oh.
Yeah.
For coding first.
Yeah, I mean the other reason was because in the part where we mentioned like the very weak bound, we wanted to add in section 5 sort of what we observed in terms of path length compared to the bound that we had on path length from section 2.
Yeah.
So it's easier to work in powers of
Okay.
2 because we have log base 2.
Yeah.
Yes. Okay. Yeah. I just wondered whether there was anything special about it.
If you pick powers of 2, that it fits the cache really nicely.
Do you suppose that if you didn't pick powers of 2, you'd get some different curve?
I don't think
because
it's
I
substantive,
did
so.
many curves. So
Okay.
yeah.
Okay.
I did a lot sort of in the range of 50 to 200.
Can I complain about the use of the word unique?
we discussed it
I think it's a typo.
about 3 minutes before we
Yeah,
walked in.
I think it's something.
I read the paper before we came, and I had changed everything to equivalence except for section 4. It still says unique.
I want to hear your complaint because I was wondering about that too.
So this may vary around different parts of mathematics. Maybe like in computer science, unique is used more like you're using it here. I don't know. But in my experience in mathematics, unique means there's one of them. There exists a unique number, positive number whose square is 2, for example. It doesn't mean distinct. And so when you say unique, I can't even remember how you use it here.
Well,
but-
so I say that the integers A, B, C, and D are unique.
Yeah,
And
and
that's
for
the
me,
equivalence class.
that's not right, because they could be anything. There are lots of integers there. They're not at all unique.
Distinct.
Okay.
Do you know, you've
That seems
probably
pretty reasonable to me.
Yeah,
read
that seems reasonable.
more different literature than I have. Do you know if it's used differently in this sense? I've seen so many people do it. I think maybe there is a standard literature that
I
uses it
have
this way.
looked online and there is not a clear explanation online of how each should be used.
So
for
maybe-
whatever
I mean, we can be very
that
clear,
means.
say A not equal to B, not equal to C, not equal to D, and then
Yes.
you're done.
So there's a phrase that's very awkward but very common in mathematics, which is to say pairwise distinct. That's
Yeah,
what I've used 100
that sounds
times.
good.
It's kind of odd, but at least it's, or even just distinct, that's a little strange. It doesn't quite say it. Pairwise distinct says what you mean.
Yeah.
And, so that unique appears about 100 times in the course of the paper.
Yeah.
And it's not what you mean.
No, that's what we were saying before because
We talked about that outside,
we
yeah.
specifically discussed it
It's
before
funny.
turning in the rough draft, and then it just ended up not being edited completely out.
That's fine.
Because I understand that it's probably quite confusing
It's just.
and
yeah,
just
yeah.
improper in
Yeah, it's
many
not quite
contexts.
the standard use of the word.
You have a lot in your paper. It's pretty interesting. Because you've researched all these different areas, the paper has the challenge of being kind of disjointed. So the question becomes, how can you structure the paper so that it isn't quite so overwhelming? One idea that comes to mind is to talk first about triangles, then about squares, then about n-sided. There may be other ways to structure it, but do think about how you can structure it so it doesn't seem quite so disjointed.
The structure we chose was integers and then reals and then observations that we didn't prove.
Whatever structure you choose, communicate it to the readers.
Okay.
Okay. So like in the introduction,
Yeah.
like we
Yeah.
first focus on
Yeah.
like the integers and then
Yeah,
the
we kinda made that.
rationals and then the reals and then interesting observations.
Yeah.
Okay.
Symmetries, I agree that it's worth thinking more about that. In particular, there are, if you're going to talk about equivalence classes, you have the equivalence classes based on symmetry, and you also at times talk about the path length is the same if one game is a multiple of the other, or if one game has a constant added to it.
Yes.
And I wonder whether it would be helpful to do more with that. It seemed a
It could
little
be
bit.
combined, I think. I mean, it's just like linearity of subtraction. It could probably be put into one little thing. What else would you suggest extending?
Are you saying that they should also be an equivalence class? Like if they have the same length?
That is an equivalence relation.
Right.
Yeah.
So my comment is, it seemed a little bit strange to me that these two different notions of equivalence were being treated in
Symmetry
different ways.
equivalence and then, yeah,
Yeah.
okay, yeah, that's true.
I would not try to combine them, though. It's just that they're different notions of equivalence that you use that imply same length.
So maybe we just prove a bunch of invariants about path lengths and
Yeah, that makes sense.
Yeah.
The game
That makes
numbers
sense.
in there.
yeah.
Right. There's also the fact that the path length itself doesn't quite make sense. It doesn't make sense for games that don't end in 0 or something. For instance, it doesn't make sense for any of the 3 games except for the ones you're calling trivial.
Well, we can just define them all to have infinite length, right?
Yes, okay, we could. Mhm. I see it as entering a cycle, and
Yeah.
maybe that cycle has length 1, which would mean a fixed point. But, yeah,
I think you get more out of it if you do it like that than just say, if you treat all games with a cycle and games that are actually have infinite number of steps to say.
Yeah, it's true. You can't distinguish
Number
between
of
them.
distinction.
Yeah.
That seems like a basic distinction between the 2.
Yeah.
But I don't think there's a unique, there's that word, solution to that problem. But using this notion of infinite game carefully, with a little more definition would be good.
So, I mean, should we sort of try to organize this in the way that, like, we show the case 1 cycles, okay, that's obvious, and then case 2 we reduce to case 1. Like, is this just going to be a proof where each case sort of like reduces to a previously solved problem?
For the 3
Yeah.
game, I would say there's this thing that you're calling trivial, the trivial game.
Mm-hmm.
We can put that
That's in its own.
equivalence class of games to one side. Then there's this interesting 3 cycle that's there, that you observe. There's a whole family of them depending on X. And then, and the symmetry. And then the basic observation is any other game, in any other game, every step reduces the range. I mean, this notion of picking out the range was a great idea that solved the problem, and putting it right up in front is what you should do. But it's not, I think that saying you're going to do this by cases isn't very informative about what
Yeah.
your strategy is. That's the
Okay.
basic objection that we have, I think.
I guess it's like proving that the range is decreasing, and we're proving that by cases, not proving the cycle by
And
cases.
also the last bit is cannot get to 0, 0, 0.
Right, that's a prior thing that has to be updated.
Right.
Right, although, and I think if you look at it, I may have made some comments about this, if you look at it, you can probably make the case considerations a little tighter. And then actually, I think there were some things that you didn't quite get. There were some not missing cases, but missing, I mean, it's 3 differences that you're looking at, and you didn't actually take account of all the possibilities. But I think it'll work,
Yeah.
but I think there's a little more to do there. I wrote that down, you'll see.
Okay.
I'd be happy to take a look at a revised proof.
Okay.
Comment on a revised proof.
Sounds good.
So my sense was that there was a sort of a project about enumerating games at the end. And I know where it came from, because we were interested in what the distribution of games lengths was. So you have this section of enumerating states, and then you get this statistics. And for one thing, I felt that the probability business in 5.3 was somehow out of place in the paper.
Whoa.
Yeah, I wasn't really sure, like if you start to throw in probability, do you have to like what amount of foundation do you have to provide for what you're saying?
I'm not sure that I would try to, I mean, when I look at this, I would never imagine that it was a normal distribution.
Yeah, we agreed on that point.
I think it might be like a Poisson something or other.
But
Well,
why
but it looks much more
expect a
combinatorial
continuous
than that.
distribution on a discrete problem?
Yeah.
That's a good point, yeah.
I mean, there's some very discrete thing that happens that causes a lot of four long games, not quite so many 6 games. I mean, there's something, it somehow doesn't look probabilistic to me. But what is amazing, see, when we were talking about this, I thought that the mode would move out as n increases.
That's what I was expecting too.
Yeah, it doesn't look like it does.
And I'm amazed to see this thing.
It's
So
like very slowly.
maybe, if at all.
It does slowly, but I mean, I don't really know if it will continue moving. Like if we plug in 2 to the 10th
Yeah,
or
or-
something, like if it moves at all.
Or if the
'Cause
rate
You
decreases.
it's
think that
the
there'll ever be more 6 games than 4 games? Ever?
I don't think so based on what we're seeing, but that was also, we only did it with n equals 256, and there's a lot of n.
So rather than do the statistics on it, I think offering some expression of surprise at that and some comment that there may be some combinatorial reason for it, which would be more, it would shorten it and be more focused on what the point is. That's my own sense of it.
These are all 4 games you're talking about?
Yeah, this is all 4. No, I used the wrong language there, I'm sorry.
I'm just trying, I'm just thinking about why it has this shape.
It's amazing, isn't it? Most games, more than half, seem to end after 4 sets.
Yeah. Great. Thank you so much.
All right, this is very good.
Yeah,
It's a nice paper.
Thank you.
A lot of fun to read.
We had
Yeah.
fun playing with it.
So, it certainly doesn't have to be longer. You've got a lot of stuff.
Right.
You could type.
And we didn't include the code in there.
That's okay.
Well, I emailed them.
Yeah.
That's okay,
So it
you don't have
doesn't
to
matter.
include the code. Unless there's something very special
Right.
about it.
Oh, it uses constant memory. That's very special.
You did?
Yeah. It's so fast.
That's actually quite interesting.
Yeah.
He was actually quite happy about it.
Yeah. Yeah.
Okay, you're aiming at quantum computation here.
Oh, wow. It's not parallelized, right? Maybe that's next.